Okay guys, so on Wednesday we talked about when we can use the normal model to approximate the binomial model. So we looked through this problem, we said that this was a binomial random variable, and we calculated the probability that at least 1,520 people agree with the statement. Next, we talked about what this would look like if we wanted to be able to approximate it using a normal model. So here's my distribution. If I'm talking about a binomial model now, my mean would be n times p, so I'm centered here, and my standard deviation is the square root of npq. And then in class we derived the fact that np is greater than or equal to 10. Quick recap of where that came from. We know that the distance here should be greater than 3 standard deviations. So from NP to 0 should be greater than 3 standard deviations. This is my standard deviation. I squared both sides to get rid of my radical. And then I divided by NP on both sides. I know that Q, remember that is my basically not P. So Q should be between 0 and 1. So here if I have 9 times Q, it's really going to be something that's close to 9. So I know NP is going to be greater than or equal to 10. Similarly, NQ will be greater than or equal to 10. So our condition to be large enough to be able to do this, be able to model the binomial model using a normal model can only happen if NP is greater than or equal to 10 and NQ. Okay? Now, the next thing we want to talk about is our textbook calls this the success-failure condition. And this really comes from the fact that if you think about N times P being greater than or equal to 10, well, how do we set up P? P is the number of successes out of my n trials. So really are my number of successes greater than or equal to 10? And it's the same idea with the failures. If I do n, it's really my number of failures out of the n total trials has to be greater than or equal to 10. And it's really number of failures greater than or equal to 10. Okay, so that's where that comes from. And now we're going to we're going to save this part for a second, and we're going to go back to the front page, and we're going to examine these situations here. So we want to know, would we be allowed to take these binomial models and be able to approximate them with a normal model? So they're telling us for all of these, my n is 20. And for A, they're saying the probability of success is 0.10, so 10%. So we need to test, is NP greater than or equal to 10? And is NQ greater than or equal to 10? So here, if I do 20 times 0.10, I'm going to get 2, which is definitely not greater than or equal to 10. So automatically, that one fails. Cannot approximate that with a normal distribution. For B, here, my n is still 20. And when I do NP, I'm going to get 20 times 25%. And that's going to be 5. So again, this fails my large enough condition because NP is not greater than or equal to 10. So I could not use a normal model to approximate this distribution. All right, here, my p has gotten a little bit larger. And if you look at this distribution, it looks a little bit more like a normal distribution. So let's see here. If we do NP is greater than or equal to 10, 20 times 0.5 is 10. So half of my condition is met for the success part. And then if we do NQ, remember Q is just 1 minus P, so in this case it's the same darn thing. So NQ is also greater than or equal to 10. So this one, we could use a normal distribution to approximate this. Here, when I say n equals 10, they're telling me my p is 0.75. So this side, with the success, is going to hold. However, when I go to test the failure sign, the non-success, Q would be 0.25. Well, I know from the other example we did, that's 5, and that's going to fail. So I could not proceed. I could not approximate with a normal distribution. Okay, so now what we're going to do is we're going to go to our original problem, and we're going to see, could we approximate that binomial with a normal model. So remember, we were looking to see if at least 1,520 people agree with the statement. So I'm going to add a blank page. Okay, and first we need to check if our condition is satisfied. So we're going to do NP, is that greater than or equal to 10? We also need to make sure NQ is greater than or equal to 10. So our N, remember there was 2,500 people in our sample, and the probability of success was 60%. Now, one thing I want you to be a little bit picky about here is don't write greater than or equal to 10 because we haven't shown whether or not that works. So just do your math, and now it works. So put a nice check mark for yourself. Now Q would be 40%. And now we know that's 1,000, which is definitely greater than or equal to 10. So we may proceed. We can approximate with a normal model. So remember, our mean was equal to NP here, which, oh, how spiffy, we already calculated. So that's going to be 1,500. And our standard deviation, if we're talking about a binomial model, is going to be N times P times Q. Okay, so I'm going to substitute that right in there. So that's 2,500 times 0.60 times 0.40. And that's going to give me something like 25.49-ish. Okay? And so here is my distribution. Hopefully yours looks a little prettier than mine. We're centered at 1,500 with a standard deviation of about 25.49. And the thing we were investigating, remember, was at least 1,520. So if we're saying at least, we're shading in this direction to the right. Okay, now we want to calculate our z-score. So this is going to be r score times the mean over the standard deviation. And that's going to give me approximately 0.82. Now we're going to write our probability statement. What's the probability that z is greater than 0.82? Okay, so remember you're going to go to your calculator for this. And here, it's been a while since we've done this normal CDF, okay? And my upper bound I did as 100. You can make it even bigger if you want, okay? And then, so that's going to give me about 0.206. And okay, and so then we can write our nice fudge factor sentence. According to the normal model, the probability that, let's see, what was the question we were actually asking here? At least 1,520 people agree with this statement is about 20.6%. So if you see here, it's not perfect, our approximation, but it's pretty close to what we got when we did our binomial distribution. Okay? All right, guys, I'll see you on Monday.